So let's move on to our first subthread of activity, mobile data. So as I just mentioned, we want to build on the geopackaging file format, which just became a standard. We're going to look at how the creation of geopackages can be automated. So a quick primer on GeoPackage. Basically, it's a SQLite-based format for storing spatial data. SQLite is it's a file. SQLite data is stored in files, but you have a SQL-based interface to work with and manipulate that data. SQLite is implemented as a library, comes on every platform that you can get. So any mobile phone, tablet, desktop operating system, Mac, Windows, Android. It's available on all of them when you buy your device, install your operating system. So it was really important for us to sort of move the geospatial world towards the more mainstream IT world, and that's why we chose SQLite as the foundation for this new universal geospatial data format. And you can store vector data as well as tiled imagery inside a GeoPackage. And some future work on GeoPackage will be to store actual coverage, multidimensional coverages in there. So it's great to have a file format, but in order to really play nice with the services ecosystem, it's even better to be able to computationally automate the creation of those files. So we had a few different scenarios we looked at for this. The first is the most basic, moving geodata from the warehouse to a mobile device. And I call it a warehouse because it really could be anything. It could be a spatial database. It could be just a bunch of shape files on your hard drive. It could be that warehouse could be any sort of data source. And you want to get that data source to a mobile device. You probably want to get it to multiple devices, and you want to make sure everybody has the same thing. And this is a scenario in the military, in consumer apps like augmented reality, and you can imagine this being very useful for Census Bureau takers, Census Bureau door-to-door census takers who get a section every day. They might get a section of the country to go out and walk and survey people, and that could easily be provided through a GeoPackage. Second scenario is synchronizing the changing data between mobile devices. So you go, you're out in the field. The Census Bureau example applies here. You're creating updates. You're getting new information. You're improving what you came out there with. And let's say you meet another person who has that same data set, or another device that has that same data set, and they've also been making changes and creating better information. It would be nice if you could just synchronize what you've been doing, and so that you don't have to go back quote unquote home to get the latest information. You can sync with whatever new device you meet out there in the field. So very important scenario from the point of view of just being able to have the freshest information in peer-to-peer networks. That importance becomes even magnified when you talk about a scenario where all the devices might not make it back home. In a military engagement, you might lose devices. They might, get damaged. People might not make it back. So being able to always keep that data synchronized wherever devices happen to meet creates a very resilient information store, information model. And just in general, peer-to-peer apps, synchronizing between peers is important because you don't want to put too much of a load on the server. Consumer-facing peer-to-peer apps could have millions of users, and you don't want to always have synchronization going through one point of failure. Final scenario is probably the most basic, building on the first. If you go out and make field changes, when you get back to the data warehouse, you want to synchronize those back in. And that's also a great place to do QA/QC. So here in the screenshots, you see some of the examples of the way participants use this. Augmented Technology is a Willow mobile app. uses can get its data not only from web feature services but also from GeoPackages now to give you a more up-to-date and information-rich view in their augmented reality environment. Luciad was another participant, screenshot on the right, which prototyped the ability to take field notes with pictures and text and save those into a GeoPackage. So what you're seeing in this image is imagery, a base map coming from a GeoPackage, as well as two little polygons, which are the spread of a plume over 2 days. Those are vector data in the GeoPackage. And then you see a picture of a harp seal, I think it's a harp seal, and a little note on that picture. And that annotation is also saved in a separate GeoPackage dataset. As you can see from that, there are a lot of really powerful, important use cases driving this work. So what we did in the end was we implemented the creation of a GeoPackage with a web processing service. Now, we initially looked at the creation of a GeoPackage as a special case of synchronizing information between devices. That turned out to be too heavyweight a solution, or too sophisticated a solution for just being able to create GeoPackage. It turns out that synchronization requires a lot more smarts between clients and servers than you get from simple GeoPackaging exercise. So at least for now, we recommend that GeoPackaging is done through a web processing service interface. And all we really did here, beyond the generic web processing service interface, is define a process called basically create GeoPackage, which gets initialized with a OWS context document. So like I said a few minutes ago, context document really describes all the data underlying a map you're looking at, all the services powering it, whether it's web map service, web feature service, web tile service, and the extent that you're looking at. So all that is described in this context document, and basically the device that wants a GeoPackage starts with a context document, says, hey, it would be great if all this data, instead of being accessed through services, were available locally in a GeoPackage so I can go offline and use it. Sends that context document to a GeoPackaging WPS with the command execute. The GeoPackaging WPS goes off, or reads that, parses that context document, finds all the services, decides whether it can read it. In this project, we implemented the support for web feature service and web map tile service. So it finds all the services in the context document it can work with, which basically means translate to GeoPackage, goes out, grabs all the data from those services it needs, translates it into GeoPackage format, puts it into a single GeoPackage, and then takes that original context document, sticks it in the GeoPackage also, but instead of the context document only having links to those internet-based services, it now also has a link, an alternative link, to get that data from the local GeoPackage. And now we have a single file, which is sent back to the client, and they can go take that data and go use it however they want, and be disconnected, be offline, and more highly performant probably, and also more battery efficient, more power efficient, which is important for mobile devices. So you can turn off the internet even if it's available. As I mentioned, geosynchronization is a bit tougher than simply a single data creation exercise. So we did a lot of research on the first few weeks and months of this project on how this should work with geodata. And we came up with a solution which I think is very important. For those of you who have been following geosynchronization efforts within OGC for a while, you might ask, haven't we been doing this already? There's a draft standard geosynchronization service out there. It's a public engineering report. It works very well. It's been implemented a number of times. The only problem with it is that it's web feature service centric. It requires you to understand Web Feature Service transactional language to understand what updates need to be made in your synchronization. Now that's great for people who are already implementing what WFS services heavily, but we also wanted to look, after all, testbeds are about experimentation. We wanted to also look at having an approach that was more service and data format agnostic. So since our primary goal here was to look at the synchronization of GeoPackages, we kind of wanted to drop that requirement for being able to understand WFS language, which would allow you to do GeoPackage to GeoPackage sync, WFS to GeoPackage, GeoJSON to GeoPackage, basically any geospatial data to any geospatial data synchronization. Another driving requirement for this was to be more lightweight and ability to recover from errors and not so tied down to a very command and control environment. So we went with an approach where changes would be eventually consistent, which is a database term for an approach to synchronization where you never know if you really have all the changes that were made, you know, when you first came or when you asked for the updates, but eventually every participant in the synchronization of a particular data set will get the changes eventually. It's important. So what that does for you, or what you lose from that, is you don't know if you really got all the changes up to the second from when you requested them, but you do get much better performance. You can, you know, always check in on a data set, see if it's changed, and it's a much more flexible, resilient architecture. So here is the basic solution we designed. The easy way to describe this is the only difference from asking for data is that, well, there's really no difference for the request for asking for data. The only difference in geosynchronization is that in addition to getting back the data, you'll also get an ID for the data set and a revision number. Having a unique data set ID is very important when you want to get rid of the idea that data sets are only in one server. If you want to be able to call roads in one server the same as roads in another, roads in a shapefile on one person's server to be the same data set as roads provided through a WFS on a government server, you have to have a unique ID. There was no way around that. And then to do good synchronization, you also need a revision number on that data set, so that, you know, whenever a change is made, it gets a new revision number. It's the only way to be able to track what's happened to the information. So basically, with that information, everything can work. That's a heavy requirement on software because tracking revisions is something which, you know, it's not just a service level change. It's really you have to think about managing your information in a different way if you're going to be able to provide a revision number on a data set. So this is why we didn't implement geopackaging as a special case of Geosync, because really, if you want to do Geosync, you have to have a real, you know, a revision-aware approach to managing your whole database. But once you do that, it's very easy. You have a get data operation where you check out the latest revision, you get that globally unique ID for the data set and the revision ID or the revision number. And then you take that data out, go happily along. Then whoever you meet along the way, you can always ask them, hey, do you have this data set also? Oh, you do? Hey, have you changed it? Do you have a higher revision number than me? Oh, you do? Okay, let me get your changes. And then we get to the get changes operation. And you're basically comparing two revision numbers between peers and seeing who has the latest. You might both have different revisions. And then you negotiate that changes process. Get the changes from You get the changes from the other person if they have a higher vision number, or you get the changes or they get the changes from you, or potentially there's a mix there. And as I said before, the previous geosynchronization work we've done is very WFS centric, using WFS transactional language. In this case, we wanted to use something which is more generic across all geospatial information. So for the changes, we went with GeoJSON as our lingua franca across geodata and web formats. So GeoJSON is, I won't get into what it is completely, but as far as its spatial information model goes, it gives you anything as complex as simple features, so it's simple features, and which covers probably 95% of the types of information that people come across. There are some more complex ways of describing space which wouldn't be covered, but those are very specialized use cases. So that's wraps up our geopackaging experiments. I'm going to move on to the OWS context work we did and focus mainly on annotation. We had one participant in Visha do a study of how OWS context can work within the US NIEM, National Information Exchange Model environment, and you can read about that in that engineering report. And we also had as I mentioned earlier, I think, report by Teradu on translating OWS context from XML, which is the only format currently approved and published, to JSON. So we're working towards having a JSON encoding of OWS context. And Teradu did a lot of good work on describing how that could happen. And their engineering report on that topic not only describes how to map context to XML to JSON, but is really a more generic rules for obtaining JSON documents directly from existing XML documents. And it identifies a lot of issues in general about going to JSON and the different ways JSON can be encoded and look as you translate from XML. There are a few different options for how that's represented in JSON. So that's a good report to look at if that's of interest to you. And finally, the third OWS context experiment was about annotation. Annotation is a topic which, you wonder why there is no existing standard yet, because it's really one of the core use cases for mapping that's existed for thousands and thousands of years. Ever since we made a map, ever since the first person made a map, I think the next thing they did was to put an X on it to show that's where we need to go, or that's where we need to attack, something like that. So we are still working on approaching a universal standard for putting annotations on a map. Now, in this experiment, we built upon some work that's over 10 years old now. One of OGC's first testbeds actually took on this challenge, and I think the problem with it was that it was too tied to particular data formats. And so we really tried to loosen up some of those requirements and create a solution, an approach that really would allow software developers not to have too much to change if they implemented this. So the important things about this are that we have a conceptual approach to annotation, which consists of three primary objects. You have the place on the map you want to annotate, and that's a real-world location. You have the annotation itself, what you want to say about that place. It could be text or pictures or both. And then you have this thing that connects what you want to say about the place, what your annotation is, to the place itself. And often, as you see in this picture, that's just it's an arrow. But there's the possibility of doing other things than just an arrow, but usually that's an arrow. So we have, and all those things are optional, except for the place on Earth you're talking about. You always need that place. Sometimes you want to just draw an X, not say anything more about it, assume that's enough. So that's why everything else becomes optional. But sometimes you want to put a little note about it. Um, and that's why you need the other pieces. So I'm not going to get too much into detail in this. Please read the engineering report. But we looked at describing those three basic objects in a sort of language native to the OWS context document. We also looked at describing that in KML and then dynamically converting those two approaches to HTML using XSLT transformation. Now, this works really well with context because you always want a base map under there. You want lots of information layers, of which annotation is usually the top. And I think this is powerful work moving towards the standard. The thing that's always held it back before, I think, is if we got too specific about how you do the styling of the annotation, how you do the colors, the line widths, the text fonts, and all those things. And I think we tried to be very smart about not going too far down that path of being descriptive or being proscriptive and preventing software from being creative and doing its best job and differentiating itself based on how it does the styling. So we describe the major elements and leave the styling up to you as a software developer.